Today we're going to talk about Java at speed, and we're going to do that at speed, or try. And it's a subject I talk about in various ways. The focus today is going to be about applying Java speed to modern deployments. And interestingly, the talk we just heard and a later talk today shows some of the changes in the things people are throwing around trying to fit Java into modern deployment environments. There are variations on how to do that. There are variations in focus, but what seems to be common is a wish to get started quickly, to be able to roll out quickly, to do things quickly in a modern deployment environment that is not just, let's run this for 3 weeks. At a high-level agenda, I'm going to talk about a little bit introduction and motivation. We'll talk about warm-up and startup and why they matter. Is there some water here? Yeah. Oh. Excuse me 1 second. Yeah. That's better. Sorry, I got off of a red eye from Kauai. So, yeah. So warm-up and startup, like that. We'll talk about some compiler stuff. And for those of you who actually want to get some technical beef, that's where the fun is. A little bit about what compilers get to do, why what they do is important. And then we'll talk more about what compilers get to do. A little more sophisticated stuff. There are things that have been thrown around about Java being slow and fat and stuff like that. And the thing that is true about Java is the first 20 seconds in Java tend to suck. But later, it tends to blow everybody else out of the water unless it's some C++ hand-coded application. Like Node.js and Java are not even close. But the beginning is different, and that's where we're going to focus today. So we'll look at what we can do with warm-up and startup in today's world and coming in the next months or years. I'll put it all together, and then I will do some bragging. I will talk about what we do, but I'm going to keep that to the end. So a little about me. I'm Gil Tene. I work on mosquito interception systems and garbage collection and a few other things. This is some evidence of me working on garbage collection. That's a trash compactor in my kitchen. It was broken. The heap wasn't compacting correctly. I had to manually defragment it. It wasn't fun, but I got to take a picture with that book. Most important thing about that picture is the date. That was taken in 2004. So I've been doing that for a while. I've built a lot of other things, which means I've made a lot of mistakes, and I've learned from a few of them. And I do tend to go around talking to people about what I've learned. At Zulu, we make JVMs, so we focus on that. We make JVMs that focus on response time and startup and all the operational behaviors. An area I like to go around and depress people about is how they measure things. You can probably find talks online with me talking about how not to measure latency, how to measure it wrong, how to measure it wrong with microservices, and everything else. But here we're talking about speed. So, speed, what is it good for? Somebody always answers that one. Absolutely nothing. But really, what do we mean when we say speed? What sort of aspect of speed are we talking about? What do we care about? And there are various aspects of speed that matter. So, for example, are you fast when it matters under load? Are you fast when a race is about to start, when the first person to the bell is the one who wins? That's two different things. Do you stay fast after the first lap, or do you take a nap? That's a GC pause right there. Yeah. If you deliver code a lot and you deploy it many times a day, are you fast even when you're deploying code, or are you just fast if nobody's changing the code? And are you reliably fast, or if you run for a while, does this happen? These are all different aspects of speed. And we would like speed to look like this. It's some number and it's totally constant, but it's not like that in any real system in the world. In the Java world, it tends to look like this. It's sort of the shape of speed over time. And we'll get into some of the interplays and what makes that happen. But this is the shape of speed in one instance of one runtime in the world. Here's two of them. Here's a few more in a cluster. And here's what happens when you roll out code. Every one of them is going through this evolution and life cycle of speed changing over time. And it's this behavior of speed and what it means to real-world deployments that we'll focus on today. So in the Java world, speed evolves. If you measure the first operation on a JVM and how long it took, you'll measure how long it took to launch a JVM. If you measure the second operation, you're probably going to still be measuring interpreted speed. And if you measure the millionth operation, you're probably going to measure optimized code. If you look at the evolution of code over time, it looks something like this. In most JVMs, virtually all JVMs that are shipping today, you start off running interpreted code, literally interpreting the bytecodes one at a time in some loop that says, what does this bytecode do? Let's emulate what it does on the machine. But we do that only for code we don't care about, code that isn't hot. Once the code has shown that it's actually being run, we notice and look at what's called a hotspot. The name hotspot for the OpenJDK JVM comes from that notion. And you look at the hotspots, the portions of code that actually execute more than once, more than 1,000 times, and start paying attention to them. And the way you pay attention to them is not directly to optimize them. It's to build a compiled piece of code that's much faster than interpreting, but is still aimed at measuring things. That's the green part, the tier 1 compiler. And its main job is to run this acceptably fast while profiling it. The threshold from going from yellow to green on a per method basis is 1,000 times around the circle. So before you've done something 1,000 times, JVM doesn't care about it enough to do anything about it. After 1,000 times, it cares enough to look at it. After 10,000 times, it'll actually go and optimize it. And it means the method that ran 10,000 times, or that looped around 10,000 times, no other code. Over time, we will find out what code is actually running enough to care about. That code will get optimized and stabilized to the point where virtually all the code that you actually run on an ongoing basis is optimized. Everything has been run enough times to do that. Initial startup, rare things don't count and don't matter. So if we look at this mix and what it does to response time over time, it looks like this. We start slow. And our code is totally yellow and then slowly changes and mixes to have a bunch of green in it, which is faster. But eventually it'll go to this blue thing that's much, much faster. That's often 30 times faster. Now, all along, we still have these other spikes, these annoying blips and stuff that may be operating system things and network things, but in Java, it's most likely garbage collection pauses that cause those. That's response time, the time it takes to complete one operation. If we want to know what speed is, we just do the inverse of this, 1 over x, and that's our picture. We start really slow, and we get faster and faster and faster, up to a point where we get to a plateau where we really are running pretty fast because it's fully optimized code. Everything is optimized when you've run it enough. But even then, we run really, really fast between terrible slowdowns down to 0 and then back to going fast enough again because we jitter and pause and hiccup and do other things. So that's the speed picture. And we can look at the various parts of it and what JVMs try to do about it. So one obvious case is if we want this to be faster, we basically need to optimize more. That's kind of a no-brainer, right? So that's where JIT compilers that create new optimizations and improve the optimization over time and figure out how to use new features in CPUs, they focus on that, raising the speed bar. And in that speed bar, Java right now is second only to roughly C and C++. Other environments don't optimize nearly as much as Java or C++ do when you get to fully optimized code. So, in comparisons to Go, JavaScript, Python, etc., it's not even close, right, when you get to that plateau. But on the way to that plateau, you're going to be executing a lot of code that isn't fast. So what can you do about that? Well, this is where we need to get a little bit into what compilers actually do. And I'm going to go into a quick crash course in basic compiler techniques. So hopefully some of you will enjoy this. And I'm going to start from C-spot run things to level set. So a compiler takes your code and it's going to morph it to code that it thinks it'll be faster, eventually generate machine code that's fast. And in doing that, it's allowed to transform your code in many ways that makes it faster. So for example, here's some silly piece of code. And the compiler is allowed to reorder this code. The code doesn't have to execute in order. In general, you can think of any compiler transformation as it is valid if you can't prove that it changed anything. If you can't show that this actually happened, then it's valid. I mean, there's no way for you to tell that I did this in a different order. So it's valid to do it, right? Certainly, if we really focus and look at that line of code, we can notice that it's actually dead. There's nothing in that line of code that has a side effect that you can measure, so I can kill it. Killing dead code is basically saying, I executed it really, really fast. Prove that I didn't, right? And if you can't prove that I didn't, it's a valid optimization, right? So you can't prove I didn't do that, so I ran it really fast, right? That's the simple one. We can also take intermediate representations and get rid of them, basically propagate the values that would have gone through variables across. So we don't actually need those A's and B's. We could just directly represent it this way. And there's another obvious opportunity there. There's just math, right? There's plus y minus y. So we can take this thing and optimize it to that. Those are all manipulations that every compiler worth its salt is going to do in any language today. Okay? These are simple transformations that piece of code and that piece of code have the exact same semantic meaning. Okay? Okay, so let's do a few more tricks that are beyond the simple ones. You can take values and propagate them across flow. And when you know what the values are, you can actually do things about the flow. So for example, here's a function or a method that has two cases for what to do about values. But we also know that the value is 5. So we can just say, since the value is 5, the beginning part of that if is never going to happen. It's always going to do the second one. Since I know that the bias is 1, that's what I return. That function is return 1. It's fully optimized. Right? That's basically taking the value 5, propagating it across the code for flow control and doing the other kind of dead code removal and propagation that we talked about before. Now, we can also do things like cache reads. So here I have a program that reads twice, reads a.x twice. It's okay to read it once and use it twice. That's equivalent. Why? You can't prove that it's not. Maybe I did it really, really, really fast, right? I read it twice. So that's a valid optimization. I don't have to go read from memory every time. And let's take that in force and say, here's a flag I read a lot, and I'm allowed to do that to it. That is a valid optimization. That's also an infinite loop. This is what the word volatile is for. If you don't want this to happen to you, you need to set volatiles on the things you do infinite loops on, because otherwise the compiler is allowed to cache this. Some compilers will try and avoid doing that because people do write this bug. So specifically infinite loops we try to avoid sometimes, but it is valid. We can also eliminate writes. So for example, if we write to the same thing 3 times, we could say rewrote so fast that you didn't observe the first 2. So let's just do the last one. That's 3 of them. How about 1,000,000? I just eliminated a loop. Right? It was writing and writing and writing. I know what the final value is. I don't need to run the loop. Right? Inlining. Inlining is the most powerful optimization there is, actually, but not for the simple reason most people think it is. Here we have a final method. Here's a call to that final method. I'm allowed to inline the method at the call site and not actually perform the call and the return. So here I eliminated the overhead of calling and returning. But that's the small part. The real power of inlining is the fact that it allows me to use all the other optimizations we talked about and many others across an inlining boundary. So let's go back to this method, but this time I don't know what the value is. However, at the call site, the value is 5. If I inline, and only if I inline, can I optimize it to that. So by inlining, I'm basically carrying the scope of what I know into the function and being able to actually apply lots and lots of other optimizations in there. JVMs and other compilers will inline very deep to unearth these kind of optimizations. A JVM will regularly inline 8 or 9 deep to extremely deep trees just to unearth all this. Most of our optimizations come from the power of inlining, bringing a lot of code together so we can analyze it. Okay, so these were the simple techniques, the normal everyday techniques that most compilers, static or dynamic, ahead of time or just in time, will be able to do. But there are some things that just-in-time compilers can do that you can't do statically. And those things have to do with speculation. The power of a just-in-time compiler is not just in the fact that it compiles in time, it's in the fact that it's able to replace code on the fly and say, that code is not valid anymore, I will replace it with other code. Static compilers don't have the benefit of doing that. What they compile must be correct. A just-in-time compiler can actually speculate and hope for something to be true that is not provable. And then if that thing turns out to not be true, it could decide not to run that code anymore. I'll go through a few examples of that in practice. Here's a really simple one. We have a similar function to before. We run it. And we ran it 1,000,000 times, and we never saw a value larger than 10. So what we want to do is speculate that value is never larger than 10. We can't prove it, but we've never seen one. The compiler will tend to emit code that looks like this. If the value is larger than 10, I still have to check. I'll do something called an uncommon trap. Uncommon trap means I really don't want to generate code for this. I don't want to deal with this. If this happens, go to the interpreter. It's not really going to happen. And if it doesn't happen, I know exactly what to do, and I'll optimize the hell out of that path. And there is a valid way to look at this that would say, well, couldn't I have just, instead of uncommon trap, put the slower code there, the non-optimized code? And it is true, you could do that. But now think of that 9 deep inline with combinatorics and how much code you're going to need to analyze. The power of these uncommon traps is they eliminate code that we assume won't happen, so we can actually analyze the rest of the code and optimize that within acceptable compute limits. So this is a common, simple optimization. Here's another one that runtimes get to do and static languages don't get to do, or statically compiled languages with no runtimes don't get to do. Every time you execute a field get in Java, what you're actually doing is implicitly that. If the reference is a null, throw a null pointer exception, but otherwise do what I told you to do. If we actually had to go and check everything we access to for a null, it would be slow. We would be checking a lot of nulls and doing a lot of ifs that don't happen. Well, the runtime doesn't actually generate this. What it does is generate code that says, that's probably not going to happen. What's the worst that'll happen? Well, the worst that'll happen is you'll give me a null, and then I'll take a signal and a segv and a segbus. But wait, I can catch that. And before I actually crash your program, I can say, where did that happen? Oh, it happened over there. I know what to do. Let's just throw a null pointer exception as if I had an if there. The runtime basically has the hardware generate the null check exception for us implicitly without any actual instructions running. This simple optimization is worth on the order of 10% of code speed on most Java applications. So it's a huge optimization. This is faster only if you're not throwing a null pointer exception. If you do throw a null pointer exception, this is 10,000 times slower than if. And the JVM will actually learn. If you actually throw a null pointer exception in a specific point in code multiple times, multiple being more than twice in current JITs, it will de-optimize this code, replace it with the code with the if, because that's faster now. But it'll only do that where you actually throw null pointing exceptions, which hopefully is not in many places in your code. Okay, a last couple of speculative optimizations that are really cool. Class hierarchy analysis basically uses the fact that the JVM is able to see the entire universe of currently loaded classes and reason about it, analyze it, prove things that are currently true but we don't know will stay true. And then it can make assumptions based on that, generate code, and if the universe changes, it could throw away the code if the assumptions have been broken. Let's use a very specific example here, because this one example is responsible for the fact that most of you hopefully write good, encapsulated, object-oriented code that is fast. And the reason you're able to do that is this one optimization. Remember, I showed you how to inline a final method before. That's easy, it's final. We know exactly what the implementation is. But here's a non-final method. And I still want to be able to inline it. You know, I have an animal, it has a color, this is how you get a color. And the universe has dogs and cats and birds in it, but none of them have overridden this method. This is the only implementer of the getColor method in the universe right now. Knowing that with hierarchy analysis lets me inline that location without having to know that it's final. And this one optimization is responsible for the fact that you hopefully do not expose your fields and you put getters and setters on them, and that you hopefully don't make them final unless you really want them to be non-extensible. This way you get both object orientation and encapsulation and extensibility at the same time, and this is exactly the same speed as a final method. There is no difference in code speed between the two. It's been this way for 20 years, but you will still find recommendations to put finals on methods because maybe it'll make them faster. Okay, so this is what happens if there's only one implementer in the universe, right? But what happens if that changes? Suppose I introduce a chameleon into the picture, and a chameleon computes the color based on the branch it's sitting on. Now I have two implementers of getColor. This assumption that there's only one implementer is no longer true. Before I can load a chameleon class, I will get rid of this code. So before the class is introduced into the known universe, any code that would have contradicted its existence has to go away. That's called de-optimization. Now, what if I still want that to go fast? Well, here's that same thing, but there are chameleons in the universe. But this code, let's say it happens to run in a dog kennel, and for some strange reason, dog kennels haven't seen chameleons. The JIT compiler will actually tend to generate code like this, saying, in the 10,000 times that I've looked at this, it's always been a dog. Let's assume it's a dog, take an uncommon trap if it isn't, and inline if it is, and optimize through. This is the power of speculation. And remember, none of this can be proven. It could go wrong in any second. So you can't precompile to it if you can't take the code away. One last example that we've recently introduced at Zulu is what we call truly final. Fields in classes in Java can be declared final, but unfortunately, there are too many things that can modify a final field, like reflection and unsafes. So generally speaking, that over there, that buffer access can't really be eliminated. The range check on it can't be eliminated because somebody could have replaced the buffer, even though it's declared final. A truly final optimization is a speculative assumption that final means final. So you optimistically say, yeah, I will optimize that away. But if anybody overrides buff in any instance of this class, I will throw away this code first. Intercept the modifiers and de-optimize code when modification happens. Okay, so these were speculative assumptions. And speculative optimizations depend on a really simple thing, on the ability to de-optimize. If we go back to this picture, the reason we have these spikes going up and down is that sometimes speculations aren't correct. Sometimes we speculate and we learn that, no, that was not a good speculation. We had to throw it away. So we went and optimized something, and then we threw it away, went back to the interpreter, and learned again, But this time, we're not going to make that mistake. So generally speaking, the compiler starts on the aggressive side. It speculates a lot, and it learns the hard way what was wrong to speculate, and stops and becomes more and more conservative over time until it gets stable. That's the general evolution. Now, that evolution will take tens of thousands of iterations. It could go back and forth and despeculate or de-optimize several times. And in those de-optimizations, we can end up with a situation where we've run just fine for half an hour and then something changed in the world. Maybe the hour is no longer 3, right? Maybe it turned into 4, and we started at 3, and we thought 3 is the hour forever, right? So many things could cause these de-optimizations to happen. There are various ways you can take a look at that kind of evolution of speed over time and try to make it faster, because we want the program to start quickly, to run into fast code quickly. One of them is to use what's called AOT, ahead of time compilation. And there are several techniques out there that do that. And it will start more quickly because it'll go into compiled code right away. However, there are a few issues there. First of all, functionality. Is this really Java? For example, can you do reflection? Can you do method handles? Can you load classes? If the answer is no to any one of those, you've just lost the ability to use about 90% of Maven Central. Because either it or something it depends on does one of those things. So, yeah, you could find applications and even frameworks built to use to work in an environment that doesn't do that. But for example, if you want to do XML parsing, I know that's not cool these days, but if you happen to have an XML config file, Spring Boot, yeah, then you need an XML parser, and XML parsers generate classes under the hood. Reflection generates classes under the hood. On the speed side, there are other things to look at. The notion of constant propagation, the ability to take a value propagated through get rid of code, depends on the value being constant. But in Java, most constants are constant only to a JIT compiler, because they are static finals that are initialized during the beginning of the application. They're not declared as 5, they're declared as get property. And they are constant if the compiler looks at them after initialization. But if you haven't yet initialized, you don't know what the values are, they're not constant. You have to do both sides of the if. And then speculation, I just explained, is hard to deal with if you can't replace code later and JIT again. Now, the best of both worlds may be an AOT that can JIT or a JIT that can AOT. In reality, that would be, both names are pretty bad because they're named for what they don't do. An AOT can't JIT, a JIT can't AOT. What you want is both. Right? One way to try and do that is to learn from the past, to basically AOT, but with a JIT, based on previous experience. A technique to do that could be done with logging and replaying of optimizations. There are various ways to do that. We do that in one of our products in Xing, and something we call Ready Now. Alibaba has something called JWarmup that does something similar. And the idea is you log optimizations from a run, and then you prime the next run with that input so you don't have to be trained on it again. You don't have to make 10,000 mistakes in order to know what to do. Another run's already done that. And then you both prime the optimizations, prime the class loading and initialization within semantics as far as you can go, maybe even prime the actual optimized codes your JIT generates if it's exactly the same. We do something we call compile stashing that does that. You can apply all that and just get faster, right? There's another technique that we are just now introducing. We're about to file a JEP on this. We're going to put this into OpenJDK, hopefully. And we call it Java on Crack. Crack here stands for Coordinated Resume at Checkpoint, not the other crack, right? Now, the idea in Java on Crack, or Crack in general, this isn't necessarily just for Java, is that the ability to do a checkpoint of a running process exists in various ways. And we're not going to say which way to use. You can use various ways to do it. The runtime could do it. The container could do it. The container management system can do it. The operating system can do it. There's a feature in Linux called Creo that does it for user processes or sets of them. There's experimental ways to do checkpoints with Docker, for example, today. And there are ways for JVMs to do their own checkpoints. Which way doesn't matter. The idea is you can take a process and just get a frozen frame of it, sort of like shutting the lid on a laptop. We've been doing that for a while, right? Then you open it up again and it keeps going. That's what a checkpoint is, right? Just suspend, resume. Now, you would, in a deployment, you would use something like your canary deployments in order to generate the checkpoint, because they're probably going to experience the world for other reasons, so they've learned what to do, what not to do. You get a checkpoint in a nice warm state, and then you replicate that 50 times and deploy it, and it'll be fast. That sounds pretty easy, except that there are a few things in the way. State. Things like sockets and files and annoying things that are hard to recreate when you open or replicate copies. And those things are, there are various things that try to recoup or regenerate some of them, but the approach with crack is to not crack that problem, but to basically coordinate around it. So instead of actually trying to say, we will make all the sockets appear the way they are, the idea is to say there will be no sockets, and we will not checkpoint if there are any. On the way to a checkpoint, we're going to tell anybody who's interested and who's registered, get rid of all your stuff, or we won't checkpoint. And on the way back from the checkpoint, we'll tell them, we're back. Do whatever it is you need to do. And if you're Tomcat, for example, you'll tear down your port 8080 on the way in, and you'll rebind it on the way out. And if you're a JDBC connection pool, for example, you'll rediscover your database and reconnect to it, and you'll fail all the connections. And various other examples like that. But by coordinating with the various resource managers, most of them are frameworks, you can get to a point where you take a checkpoint of a process that has no external state, and then you resume it and tell everybody in it, okay, you're back, recreate, reconnect everything. Again, looking at a laptop, it's exactly what web browsers have been doing for a decade plus, right? We don't actually expect the existing TCP connection that we had when I shut my laptop down in Kauai earlier to exist here. It's going to recreate it. Now, what does that mean from a time perspective? Here's some prototype numbers. And what we did is we took Micronaut and put it on crack, and put Quarkus on crack, and took Spring Boot on crack. And even went into the XML transform service that really needs to do real work and put it on crack. And we compared the time to execute on a regular JVM from nothing, from a standing still start, to one of starting the same thing on crack. We also compared to the Graal native image, which some of these, especially Quarkus and Micronaut, are using for the quick starts. You've seen a demo of this earlier today with the native image stuff. And just highlighting the numbers there, yes, GraalVM does start faster than a OpenJDK full-featured thing on crack, but by a difference that is so minute that it doesn't matter. So it's a difference between 1% of the time and 3% of the time. I'll highlight the fact that starting a Docker container takes half a second. So we're in the noise of the noise levels between them. The other useful thing here is, does this work? Maybe it will. Maybe. There it is, yeah. Is that if you look across these, the numbers are almost the same across all the different applications. It doesn't really matter what you do, because basically you're jumping into the checkpoint of a running image, jumping into code that's being swapped into memory as fast as you can take it, and as your code flies around. We don't wait for the entire image to be read. It's just on-demand pages in, and boom, you're up and running. So this technique seems to be working well. It does require this coordination API in order for various frameworks to be able to coordinate with it. In each of those cases, we touch some code, on the order of 50 lines of code in each one of those, in order to do the coordination. Register interest in knowing about a checkpoint and a restore, doing the right thing, going into a checkpoint, doing the right thing, leaving the checkpoint. And that's what crack is about, coordinating the restoration of the process. What does this mean to the startup behavior? Well, if we start from this kind of behavior, you take a while to start, then you go slow and you get faster and faster, and then you get this boom, the optimization where real load hits you because it has behavior that's different than what you assumed in your small warm-up. Mostly you want to get rid of the de-optimization storms in that case. And for that kind of thing, avoiding de-optimization simply by logging the history of optimizations and the pessimism that you should have learned does the job pretty well. Ready Now does that, JWarmup does that. If you do it all the way, you can get to basically hitting the ground running on the first operation. So you start up, and when you're ready to go, you jump into traffic, you run into traffic, not in interpreted mode, but at full speed compile mode. And there are various modes to actually hold you back. For example, not letting main start until all the JITs are done. So that when you jump into traffic, when you agree to take traffic, you'll be fast. But there's still that annoying, it takes a while before you get there, right? Because the whole thing needs to start up, the JVM needs to initialize, the compilers need to do their thing, the classes need to be loaded. That's where the instant on nature of crack comes in. You go and you bypass the entire set of loading classes, initializing stuff, and the first 20 seconds of the application thinking about things, and just jump into a running mode that was just saved as the mode you want to run in. So if you take a look at what this means from a behavior point of view, improving the JIT speed will get you higher speed. Doing these various quick start techniques basically moves it up to an almost instant on behavior. Now within this, there's this last part that is, these spikes, not really related to the code speed parts, but they're still about speed because you don't want to be stopped. And if you eliminate GC pauses, you'll get that nice flat behavior that we said before. At this point, I said I'm going to do a little bit of bragging. I'll spend all of 4 minutes doing it. Hopefully we'll be good on that. So to start with, I work at Zulu. I started a company, and we're all about Java, right? We have various JVMs, and a bunch of people use them. So these are just samples of them. The two main product lines that we have are called Zulu and Xing. You can think of it as Zulu is about OpenJDK offerings that are the current 100% open source, same as everything else, just a little ahead of the curve, but everything is within the project. And Xing is about being better, faster, metrically improved. The Zulu offerings have a few groupings. First of all, there's a free community offering. It's 100% open source. It's 100% free. It does all the different variations of Java, and it's actually the longest track record OpenJDK build out there that has things for multiple platforms. Notice that we have Java 7. We've just recently retired our Java 6. Other people are starting to talk about whether or not they do 8 or 11, right? And that means, we've been around for a while. Our 7 will still be around for a few years because some people are still running it. The same will be true for R8 and R11 and our numbers after. We also have the most platforms of anything out there. All the different development platforms in Linux, all the different types of packages, including, for example, Alpine native muzzle, not glibc implementations for people who want the smaller footprint or the smaller attack footprint of the other libc implementations. Zulu also tends to be ahead of the pack on the latest features. So to give you specific examples, right now, today, Zulu 8 is the only OpenJDK implementation you can use that will let you use Java Flight Recorder for free in production right now. You can download it, it's there, it's free. This is being upstream. We're coordinating with the OpenJDK project. Eventually everybody else will have it, but we're probably a couple of quarters away from that. And we've had this now for a quarter plus. So if you like Java Mission Control, you like Java Flight Recorder, Zulu is the free JDK you can use to do that. We're announcing today or tomorrow? Wednesday we're announcing. So here's the pre-announcement. TLS 1.3 support for Java 8. When we talk to people about Java 11 versus Java 8, we support both of them just fine, but a lot of people are having a hard time moving to 11. The number one thing they tell us they want from Java 11 is TLS 1.3. Well, we now have TLS 1.3 support in Java 8. Out of the box, no code changes needed if you want that kind of thing. And again, this is an open source thing. It'll be available for everybody else and hopefully upstreamed in OpenJDK 8 in general. There was mention of containers restarting JVMs because of limits and policies. Zulu was the first OpenJDK build to support the actual cgroups limits, and it did it a quarter or two ahead of the other OpenJDKs. Everything we do eventually gets upstreamed in open source. This is not long-term differentiation. It's just that at a given point in time, this is probably the JDK you want to be using. Then we have Zulu Enterprise. Zulu Enterprise is really easy to understand. It's a supported version. It's still 100% open source. But this is what enterprises get if they want things like SLAs and security fixes and the right vehicles for urgent security fix and out-of-cycle stuff and all the other important things. It's also where you go if you want actual guarantees, contractual guarantees of long-term support. I mentioned that we have Java 7 and Java 6. We've been around for a while. We're going to have 8 and 11 for quite a while, and 17 after that. We've also introduced something we call an MTS. That's midterm support. Midterm support is about allowing you to take some of those interim Java releases between 11 and 17 to production. For example, Java 13 is planned to be a midterm support release for Zulu Enterprise, which means we will support it until 18 months after Java 17 is out. You will have overlap. You can go from one production to another production stable and not have to cut over every 6 months to something that was released last week. We think that that is what's going to make it practical for people to actually take Java 13 to production, because otherwise, what do you do when Java 14 comes out and there is no more Java 13? Do you go to that release that's a week old, or what? You know. Then we have this Zulu embedded thing that's for embedded stuff. If you want to redistribute software or make devices, we have a whole product line for that too. So that was Zulu, probably what most of you would be looking at. Xing, as I said, is about bragging with metrics, right? So here's some metrics. This is Spark running the TPCDS benchmark. This is 90-some different queries of TPCDS and how we score compared to OpenJDK on them. The average of this, the geomean, is 24% faster. That's 24% less CPU or fewer machines or smaller AWS build to run the same Spark workload. So it's simple. Our garbage collector is something that's pretty unmatched out there. It's been around for a while. People probably know us best for this. Yeah, that's the 1 millisecond line for Cassandra and AWS. And we have this Ready Now thing that's been around for a while, focusing on this problem. And fundamentally, it's about reducing the number of things that get hurt when you deploy code. So when you deploy code 20 times a day, that happens 20 times a day. And every one of those dark spots is a hurt transaction. We reduce that, not to 0, but by an order of magnitude or 2. And in fact, this is the picture you would have if there were GC pauses. Since Xing doesn't have GC pauses, the picture looks like this. And last, in production, things look like this. This is an actual transition on a live cluster from OpenJDK to Xing, showing the impact on success rate of operations under load. You're looking at an entire week. The load, you can see the weekend, you can see the week after each day. And the orange line is simply the 2%, top 2% of success rate, from 98% to 100%. You can see that under load, things kind of crack a little. When it's low, they recover. And over there on the right is when they simply rolled the cluster one node at a time to Xing, and everything went to close to 100% success rate on the same machinery. That's 99.98 success. It's not 100. What that meant is not just that the success rate is much higher, but the carrying capacity is much higher. They were able to get rid of more than half of their AWS instances and still carry the load. So this is an example of this basically in production. Now that's it for my advertisement and bragging. I apologize for that last part, but it is part of my job. Hopefully the beginning part paid for it. And with this, I'm not sure where we are in time, and if we want to do questions, go out to lunch, whatever those are. Lunch. Okay. Thank you, everyone.